Hello and welcome to the annual American Conference on Pharmacometrics. I'm Ivan Borisov, I work as a developer at InsysBio, and this video will guide you through our poster about building secure and scalable computational environment for QSP modeling and simulations. If you are watching this video while the conference is on, I also invite you to visit our booth and learn more about InsysBio services and tools, and share your experience and your thoughts in the field of QSP modeling. If you came across this video when the conference is already over and you have any questions regarding this work or other projects by InsysBio, don't hesitate to contact us. The contact information is provided right below this video. The goal of the study is to propose a software and hardware solution which can address one of the main computational challenges of a QSP project, namely provide the users with a secure and easily extendable environment to both develop the models and run computationally demanding simulations in parallel. The proposed solution can be best illustrated by the following scheme. All components of the computational environment are deployed in the secure cloud infrastructure. In the current study we use Azure Cloud, but in general it can be any cloud provider with necessary security certificates. The main component of the infrastructure is user's workstation with pre-installed software tools for models development and simulations. The core pre-installed software component is HETA. It consists of three parts, namely HETA language, which is a DSL for models development and annotation, HETA compiler, which enables the users to export HETA model into different formats like DBSolve, MRGSolve, SBML or Julia, and HETA simulator, which is a Julia-based open source package to run simulations and parameter estimation. HETA simulator relies on ODE solvers provided by CML package ecosystem and utilizes Julia ability to easily execute code in parallel. The modeler accesses the workstation, develops the model, and runs the simulations. When the capacity of the workstation is not enough to satisfy the needs of the project, the user can easily scale up the available computational resources. He calls Kubernetes API through Julia-based package Key8 clustermanagers.jl and deploys additional Julia workers. In the current study we use serverless virtual node, which allows us not to manage the underlying infrastructure. Container instances with pre-installed Julia and HETA simulator are provisioned, and once they are running, they connect to Julia master process on the workstation. When the connection is established, the user can run simulations in parallel on deployed Julia workers. Then the user can save the results and terminate compute instances. The results of the simulations can be shared with other project members through secure data sharing server. It can be SharePoint, for example. It also can be used to upload sensitive data like clinical data, which is required for models validation. Now let's have a look how this actually works. The application of the proposed environment will be demonstrated on the use case of virtual patient simulations for COVID-19 model. I'm accessing the workstation where I'm able to develop the model and run the simulations. COVID-19 model is written in HETA language and it is freely available in InsysBio GitHub repository. As I have mentioned, HETA compiler can convert HETA models into different formats like SBML, MRGSolve, MATLAB, DBSolve, and Julia. To run the simulations in Julia, I have loaded HETA simulator package, and now we can call load platform function to convert HETA notation into Julia code. Platform is a HETA simulator object which can unite different models to run multi-model simulations or fitting. Once the model is uploaded, we can define simulation scenario, run the simulations and plot the results. The capacity of the workstation is limited, so in order to run more computationally demanding procedures, we need to extend the workstation resources. A natural example of such computationally demanding task can be generation of virtual patients. Typically, it requires running thousands of simulations in order to obtain a plausible virtual patients cohort. Ability to run the simulations in parallel drastically speeds up this process. So let's provision additional resources to generate virtual patients. We call Kubernetes through K8clustermanagers.gl package to provision remote Julia workers. Certain modifications to this package have been stored into distributed func script in order to use it with Azure Virtual Node. We provide a link to the Docker image with precompiled HetaSimulator package and run add_procs function to provision 50 Julia workers. It can take a couple of minutes for the containers to be created, so we can have a cup of coffee in the meantime and come back once the workers are connected to Julia Master. As all the workers are up and connected to the master process, we can run parallel virtual patient simulations. We activate HetaSimulator on all the workers. It takes less than a second because HetaSimulator was precompiled and provided as a systems image at worker startup. We set the number of iterations, define parameters distributions, and run Monte Carlo MC function. HetaSimulator internally relies on Julia differential equation packages, so the user can choose one of many ODE solvers and set up other solver-related options. Differential equation packages also provide a nice way to choose how the Monte Carlo iterations are distributed across workers. Here we use basic Ansible distributed setup. The first iteration takes some time as modal code is compiled on each worker, but then workers use precompiled functions which speeds up the process. So let's wait a couple of seconds more for the simulations to finish. As the simulations are completed, we can terminate the workers. The results are stored on Julia Master, and now we can save them in table format, plot statistic summaries, extract parameters values which are potential virtual patients, and proceed with further analysis. The proposed architecture allows the users to both develop QSP models and run computationally demanding simulations like virtual patient generation in the single, easy-to-use environment. This environment supports unlimited resource extension by adding new compute instances on demand. The security of the proposed infrastructure is guaranteed by cloud provider's certification. The infrastructure is OS independent, and it allows the users to develop the models on the dedicated workstation in the preferred environment, like Windows, and run simulations on the most performant compute instances. The solution also allows customers access to the environment and participation in the model development process and simulations. Thank you for your attention. We will be happy for any questions and feedback. Don't hesitate to contact us. insysbio@insysbio.com.